first one. So three-dimensional coordinate systems. All right, so we're used to the 2D, right? The XY plane or the rectangular plane. So there's lots of different names for it, right? 2D, X plane, rectangular plane, what's it called? Cartesian plane is another one. And as we know, right, each one is represented as an XY. So here's our simple XY plane we all know, right? You guys have been doing this since what, first or second grade, right? When it comes to it. Now, when it comes to a three-dimensional plane or 3D or space, that's another one interesting. So we're going to talk about space. Okay. It's an XYZ plane. Now, this is always going to be the case in our class. It really just depends on the class. If you go to physics, it changes a little bit, but not that much. But for our class itself, this is how our coordinate system is going to be. X is going this way, Y is this way, and Z is always going up. So again, remember these are lines, so the negatives go this way. So this is the positive X, positive Y, and positive Z. So therefore, the negatives will just go in the opposite directions. Yeah. Again, like I said, it changes when if you go to physics. I believe physics sometimes even have the Z scale here and the Y scale there. It really just depends on itself. Yeah. But again, for our class, we're going to follow something called the what's it called? The rule of thumb. There we go. So if you just have your fingers, so they basically say this side here is the Y, this side is the X, and your thumb going up is going to be the Z. So that's pretty much how they do the 5 rule of thumb. And again, it depends, depending where you go, this rule of thumb changes, but that's usually the case when it comes to the scale itself. So interesting little fact there when it comes to it. Okay. Now, when it comes to our 2D-dimensional plane, right, we have quadrant 1, 2, 3, and then 4, right? However, when it comes to the 3D-dimensional plane, we actually double that. And it's an octet. Okay. So we actually have 8 planes. So the first plane you could kind of see till here, you could kind of like look at it. We have the ZY plane here. So just like a piece of paper on here. Next one is here. Next one is here. And then that's just 3, and we have another 5 more on the back itself. Okay. So again, we have octets in XYZ plane and 4 there. So when you guys go into if you guys go higher in mathematics, and you go into what's that class? Differential equations and all that, you get into 4D, 5D. So it just ups the scale from there. So it usually just goes exponentially because it's an exponential portion. So interesting fact there as you go higher. But again, don't worry, we're always going to be dealing with the space or the 3-dimensional space, so in actual life scenarios itself, which is pretty cool. Okay. All right, so let's talk about something I said earlier. Now, surfaces. So we're used to the XY coordinate system, right? But in the 3rd-dimensional spaces, what is these things are called, right? So we have planes in the XY plane, right? The actual planes, right? But what is this called in 3 dimensionals? And that's what's called a surface. Okay. So whenever we have a point or a line in a 3-dimensional plane, we always are generating a surface. So for example, let's just graph the line y equals 5. So again, if we just go back to our normal XY plane, right, here's 5. So this is our y equals 5. Right, we just get a line. Okay. Now, if we transform this into the XYZ plane, again, this is the positive y-axis. Again, we always just graph the positive values. So there's 1, 2, 3, 4, 5. Okay. Now, in here, right, if we do a t-chart, x could be anything it wants to be, and y is fixed to be 5 no matter what, right? So like 1, 5, 3, 5, negative 1, 5, and so forth, right? Because it's a straight line, a horizontal line. So the same process comes into play here. So on this scale, on the x value scale, and again, going in the opposite direction for the negatives, we get the line itself. So that hasn't changed. However, a point on the XYZ scale has 3 points. Well, again, X can be anything I want it to be. Y is always fixed. But we also have the Z scale going up and down respectively. And again, this could be anything I want it to be as well. So we actually get two things going up. So I actually get this going up on the positive Z scale, and then going down as well. So I didn't make it nice and pretty, but technically you just get a piece of paper. And it's called our plane, or our surface in three-dimensional place. So it literally is just like a line, a piece of paper just cutting exactly at y equals 5. So I should have done like this. There we go. That looks better. So this is why this class usually gets more difficult, is just be able to graph things to visually see what's going on, because most of the time it's so difficult to figure out what this curvature and what this surface will be and look like. And that's pretty much the hardest part, is figure, okay, given this weird surface that I don't know what it looks like, now apply this new mathematics to it. Okay. And again, we'll try our best to go through this portion as well together. Any questions so far? Okay, assume that's a no. All right. So again, we're not going to go too much in detail, but I do want to give you guys a couple things, or a couple examples of how we know from regular stuff, and just put it onto the three-dimensional plane. So given the points, graph each one that satisfies these. Now, hopefully you guys remember, but probably not, right? So a circle, our general circle, is x plus y squared is equal to r squared if it's centered at the origin, right? So in this case, that's exactly what we have here. And we also have to generate its z equals 3. So we have a line at z equals 3, kind of like we have here, that also generates a circle as well. So the first thing we do is goes on the z scale to 3. And since we know, again, if I just go back to our regular ed scale, right? This is a circle centered at the origin with radius 1, right? This portion there. So all we're just going to do this translate here. Well, this now is instead of flat, it is now this way, right? An actual oval. So it kind of looks like this. Sitting on z equals 3. So now we have an actual circle that's centered at z equals 3. So you can kind of like translate it here. Where this is 1 and this is 1. Okay, so pretty interesting stuff. And this actually is a way we do b as well. So now what if we don't have the restriction of z equaling 3? So what we want to do is, what's the surface of just a regular circle? Well, it's exactly that. Now z could be anything I want it to be, just like on the plane here. So I literally just get a cylinder. So that is how cylinders are created in these XYZ plane. So like I said, just quick little examples to show you guys how things are created and drawn using stuff we know on the XY coordinate plane to the surfaces in the three-dimensional plane. Okay. All right, distance formula. So the distance between any 2 points or in the three-dimensional planes, it follows the exact same equation as normally. Again, just notation purposes, you just got to be careful of. So our considered absolute value, right? Because if we do this, for example, this is called the absolute value of x. But when it comes to those lines given 2 points, that's going to be called our distance itself. Okay. So given points P with x1, y1, and z1, and the other point x2, y2, and z2, we get this being our distance formula, which is again just follows the same thing. If I just put that's our z distance formula in regular itself. So the good thing is a lot of the stuff you've already known, we're just going to apply it and just usually just tack on this stuff at the very end, most cases. And you'll see that very similar when we go into integration, derivatives, and then double integration as well, and double derivations as well. And the last thing we're going to talk about is just before we finish this section is equation of a sphere. So just in case you weren't sure what an equation of a sphere is, because well, again, we're going to talk about a lot in this class, is given at the center of H, K, and L, and radius R. Again, if I cover that up, that's just the equation of a circle. So the radius of a sphere, I mean, the equation of a sphere just gives you the z scale itself. Okay. So to finish up, I just give you guys a quick little example of using the distance formula. So find the distance from the points 4, -2, 6 to the xy plane. Okay, so I'm not going to do this all the time, but since we're doing the first section, I just want to show you guys what does it mean by to the xy plane. So first, let's graph this. So roughly, this is going to be 4. So remember, that's x, y, and z. So 4 this way, 2 back, because the y is negative going back, 2 back, and then up 6, so roughly here. And we want to see how far is this distance to the xy plane, meaning this plane right here of the xy. So basically, this distance here is what we're looking for. Okay. So we're given our first P, right? 4, -2, and then 6. The question is, what's another point going to look like? Well, remember, it's a straight line going down. So on the xy plane is just pretty much the same thing, except we don't have a z. So it's just 4, -2, 0. And there's our 2 points. And this applies for anything, right? If I just change this to a zy, you do the same thing, or xz. So now you're doing here, and you find that distance as well. Well, that just is basically 0, but you guys get the picture. So now that we have our 2 points, we just simply find the distance and call it a day. So the distance is a P1 and P2. And I'll call this 1 and then 2. So 4 minus 4 squared plus -2 plus 2 squared. And then plus the z's. So 0 minus 6 squared. So notice everything pretty much cancels except for the last one. So you get 36. So the distance is 6.